Hi everyone, today we are going to discuss the Physics 2211 Lab 2, which is the analysis of a motion of a falling object. I am Aditya Vora and let's get started. So the table of content include introduction and purpose, formula used, experiment, code without drag, code with drag, and the combination of all three models, along with sources of error, what if and what else. Let's start with the introduction. So the purpose of the experiment is to observe the motion of an object dropped from rest which is somewhat traveling slow. The aim is to investigate the effect of gravity and the second case of gravity plus drag on the object's motion. The analysis of a paper ball is with a mass of 5 grams using the tracker and computed by a computational model coded in GlowScript. The experiment focuses on the Newton's second law, which is force is equal to mass into acceleration. The system is the paper ball. The surrounding is anything else except which interacts with the system, which is air, earth, gravity, or even the person who is throwing the ball. So as you can see from the figure, a drag force acts in upward direction, whereas the gravitational force acts in the downward direction. The review of the result is shown here, which we'll discuss further as going into the video. The formula used is the Newton's second law, which is F is equal to ma, velocity update formula, position update formula, and the momentum principle. The forces acting in this experiments are the forces of gravity, which is 0 minus mg is 0, and the forces of drag, which is 0, v square, and 0. Thus, we can see that the force of gravity is acting in the negative direction, whereas the drag is acting in positive direction. F net is the force per drag plus the force of gravity. The experiment. As we can see by the video on right, I threw a paper ball from a distance of around 50 centimeters and I used the tracker app in order to determine the position versus time graph. The system is the object and the surrounding is the air, atmosphere, person, anything which interacts with the system. The initial conditions, as we can see, are the mass of the ball is 0.05 grams, the initial position is 000, and the initial velocity is 000. The delta t is taken as 0.017 and g is taken as 9.8. Code without drag. So now we'll look at the code without drag. As we can see, that the delta t is taken as 0.017 seconds and the force acting is W, which is minus mg. As we know, the only force acting is the gravitational force, which acts in the negative y direction. The position versus time graph, along with the velocity versus time graph, is shown here. Now we look at code with drag. As you can see here, the initial condition remains the same, only the thing which changes is the B. B is basically the coefficient of resistance, and hence it was after experimentation was taken as 0.04. As we can see, there are two forces acting, which is the drag force acting in positive y direction, which is minus B times magnitude of ball velocity times 2 times norm ball velocity, and the gravitational force which is acting in the opposite negative y direction, which is minus mg, and hence the F net is the force of drag plus the force of gravity. We have also used the position update as well as velocity update formula. Velocity versus time as well as position versus time graph are shown below. In thus, now we have compared all of three models, which includes the blue, which is the experimenter model, the red, which is the drag model, and yellow, which is the drag model. The magnitude of acceleration decreases under the presence of air resistance and finally becomes zero when it approaches the terminal velocity. In absence of drag, the magnitude of acceleration remains constant, and hence, as we can see, the model with drag matches much more closely to the normal experimental conditions. Now let us look at the sources of error. Sources of error could include inconsistent calibration of the object. The ball, being a non-uniform object, can change, and hence the B would not be perfectly accurate, and inaccurate value of G. What does it mean? The model with drag predicts the terminal velocity, which is the asymptote, as we can see here. The net force is equal to 0, thus the object would experience no acceleration. Now let us answer the what-if question. What would happen when the object was initially thrown downwards? Would the terminal velocity in this case be same or different? So no, the terminal velocity will remain the same because it starts with the initial velocity, which is Vi, and thus the air resistance is tied to that. Thus, no change in terminal velocity, but the time required to reach the terminal velocity will increase. Thank you and have a nice day ahead.